I'm going to be talking about the jitterbug. A little bit of history. We go back into the 1500s, and I'm following sort of one track of history because you can go back a lot further. You'll find around in the 1550 that there was some studies being done of close packing of spheres in order to get a sort of an understanding of how they were arranged, and it was beginnings of the idea of atomic theory, or atomic how atoms were arranged. Kepler, of course, tried to demonstrate by using close packing of spheres the snow crystals, and as you see from the graph illustrated here, that there was smatterings of work that was done around this type of idea of packing of spheres. In a very, well, you know, there was little jumps here and there, but something happened here. Something happened in this region to where all of a sudden there's a jump in people who are experimenting and looking into and thinking about the sort of the close packing of sphere problems and things, or activities that were related to that. And one of those I call your attention to is 1939 with the general treatment of crystal dislocations. And then in 1944, Fuller, and the diagram that you see in the background is Fuller's idea where he was playing around with the packing of spheres on a variety of forms, and you'll see a little wave running through this. And this was the introduction of the first thought that he had about motion, and in that case it happened to be wave motion, and he wrote a treatise on the reciprocal motion of G internal sphere propagation waves. Then, if we sort of stop there, because in that graph, that's where you started to see that recline or incline. And in 1939, which is along that same region, there was a fellow named of Burgers who started or published a report on screw axis transformations in dislocation, crystal dislocations. Now, there he was talking about the arrangement of atoms and so on going through a rotation translation in a screw axis motion in that set of studies. And following him, Berger, in 1947, talked about displacive transitions in structures. And the diagram that you see here is his explanation of that displacive transformation going on. And right at the same time, Fuller was studying and working with close packing, and he started asking the question in the packing of spheres, what happens if you remove the center sphere? And he saw a collapse of the spheres into a new close packing position. The displacive transformation that Berger talked about basically is the transition transformation is a transition in which the displacement of one or more kinds of atoms or ions in a crystal structure would change the lengths and or the direction of the bonds without severing the primary bonds in the atomic structure. In this particular illustration, you see across the top you have square sets that retain the length of the edges in the set, but the bond angles change. And so this is one form of a displacive transformation, and that Berger was studying. And what you find is that in that form, you have two simultaneous operations, a rotation and a transformation going on simultaneously, like you see here. Okay, you have a rotation. Now, in this model, it's a little bit different than what Berger was working with, in the sense that he was looking at single sets. What I've done is I have a double set, which shows the left-hand, right-hand rotation in the transformation model. Another example of that is more kin to what Berger was looking at, because he looked mostly at this type of a structure, which is the transformation of the tessellation squares. So you have a rotation, translation, going on as the operation within that form. Now, the displacive transformations, and those are the ones that I showed there, a fellow who got together with Bucky Fuller about the same time when he was at Black Mountain College, but taught in the design architecture, I guess, school at North Carolina State, and his name was Duncan Stewart. Worked with Fuller in the Fuller Foundation, get Fuller set up just specifically for this purpose, or these kinds of purposes. And he was looking at these conceptually and started to catalog different forms. And what he worked on in that sense was that there were, he broke it down into 3 different types of transformations. One of where you did a connection of vertex to vertex connected face to face through a vertex. He also connected face to face through an edge. And this is the transformation there. And then he did one, a vertex to vertex through a vertex. So you can kind of see the direction it goes. You retain the properties of the vertex, but you make the connection to the face by going through this vertex. So those are the 3 transformations were being studied. During 1962 and 1972, under a NASA contract, I started looking at these with doing a mathematical modeling to try to explain the transformations were going on mathematically, whereas Stewart primarily was doing it through conceptual modeling. Ron Resch was sort of paralleling the work that I was doing, but he became eventually pretty engrossed into this form, but he was doing it through folding paper. So he was working through plates and plate geometries and trying to see if the transformations were going on there. And you'll see a diagram of one of his models that he was doing at that time. The animation is an example of a full 360-degree transformation, and it's kind of interesting because when it starts out on one side, it goes all the way across, comes back to this point if you allow the rotation to be a full 360, and given the restraints, it has limits as to what those restraints would give. So mathematically, the space transformation may pass through a 360 rotation cycle, and where the polygons are allowed to basically become congruent in the process. All right, now, one of the things that was interesting from some of Arthur Loeb's studies is that he basically discovered that the displacive transformation does not need to be limited to regular polygons, which was quite interesting. Up to that time, the polygons were all regular, triangles or hexagons or what have you, and it was interesting that he got into it. Now, one thing that's interesting as well is the general forms show up in many mathematical articles, but under other circumstances. They don't introduce the motion. Okay, it's when they're studying tessellations and packing, all right, and it shows up all through the literature, the diagrams, but for some reason or other, people haven't picked up that they can be animated, or they can undergo this transformation in these the models. So you'll find people like Grunbaum's and Shepard's book on tiling and mosaics and so on, but we'll never talk about the possibility of doing a rotation, translation, transformation for generating many of these forms. So the diagrams that you see here are very common throughout the textbooks, but rarely do you see someone who talks about it in this light. Now, right about that same time, Fuller was playing around with the close packing of spheres. And and he was sort of experimenting with and trying to understand things in the area of nuclear physics and chemistry and quantum modeling and that type of thing. And that's when he made this connection from the close packing of the spheres, and if you remove the center sphere, then it went down to the hexagonal close pack, and through that phase was the octahedral phase. So if we take this model here, you can see that as you go through a transformation, that a mid-phase is the icosahedron. So you have the cube octahedron at this point. You stop here. You have this distance from here to here is, now I'm doing a uniform transformation, so that's why you can do all the other 6th degree of motion in there in the model. But if you do a uniform transformation, at that point, you have the icosahedron, and then eventually on. Now these are the areas that Fuller studied and Stewart studied. Well, this is another one of these transformations in which they followed, Duncan Stewart, myself, and Fuller, was also studying this connectivity between edges, or face connection across here, an edge connection from face to face, and through the vertex. And that's what we see in this case. What I added to the fact is if you look at Fuller's aspects of the study, they were dealing with a single face calculation on the arrangement with the polyhedra. Well, and in some cases where you have an odd number coming together at a vertex, somewhere you have to have a sinus. You have to open that to keep the circuit, so you don't have closed circuits in all of the polyhedra. However, if you double up and do the rotation in a clockwise and you do the rotation in a counterclockwise, so that let's say the inner face goes in one direction, the outer face in the other direction, now you can build a complete circuit because you always have an even number coming together at a vertex. So, bingo. And it gives stability. Though it doesn't behave like the one that is a single face, and that is dependent upon the two faces sliding against each other that starts to do that. So you don't have this kind of relationships anymore. As soon as you do that, these become a complete stable unit without any external supports or internal supports to hold it. So, very interesting. But you study those with a face connection. You can also study them as a face-to-face through an edge connection. And that's what you have in this model. And these are all of the tetrahedron with the three different methods. Or, and this one's not quite a good enough model, but it will demonstrate the idea, I think, that you can see the vertex connection where I'm coming down to a vertex. So this is connecting to the inner one, and you have a transformation of the vertex transformation. All right, now basically what has been done is a classification of these as a family of polyhedra. You can start with the tetrahedron, for instance, tetrahedron to the octahedron. Now if you place the faces in place, you go from the octahedron, you pass through an icosahedron and then also into the cuboctahedron. The icosahedron will expand into the icosododecahedron. And by starting with this, you'll find a whole family of polyhedra that you can go through that will start with the tetrahedron in that process, and you can account for all of the regular and semi-regular polyhedra and many others in other that have shown up in other classification systems. And in addition to that, you'll find that the close packing models have also been studied. This was the original, or picture of the original model that Fuller did with, or actually Duncan Stewart made it, but with Fuller in 1949 of a space filling process. And here's an animation. This one's done by Adrian Rossier in 2006 that basically shows the capability of going through a full 360 degrees. And when you do that, you'll notice it goes through a phase in which it inside outs. So if you watch, you'll find that the colors change when they come back up. Now you're red, come through, now you're yellow, you go back through the system, come back to the original position through a full rotation of any single phase. And by doing this kind of transformations, you find that you will go through phases of many of the stellated forms as well. So you start defining the what is known as the stellated polyhedral forms. In addition to that, Yamanos in Japan, and you can find this as a commercial item called the Juno spinner. He has found other methods of making the linkages of the connectivity, but using the same basic transformation to get through the same forms. And this is an example of some of the work that he's doing. All right, now you'll find that in the tensegrity forms that the jitterbug is also starting to show up and can be modeled. And here's a sort of an interesting model of that. Here is the tensegrity of the sixth strut that so many people are familiar with. But if you make the connection and put a face in this position, and then you allow this to reduce its size, but you keep the tension member the same, then it will force that face into the jitterbug transformation. So it goes through those stages. And I've often wondered, since people like our good friend Bob here and Grip and so on, who have done some classifications of tensegrities, that if they approached the jitterbug transformations, that there might be another way of looking at classifications of tensegrity systems. Just another one to add to the collection of, that's been done. Also, an interesting thing about the duality transformations, what you have here is an animation of the connection of the duals. In this case, it's going from the face of the center of the face of, let's say, the octahedron to the center of face of its dual, and it will go through that transformation well. And there's a small kit on the market that we did back in the 1970s that we call the OmniStar, which goes through the same jitterbug transformation. All right, now what basically we did was put this into some form of mathematical model where you could study the transformations, and fundamentally what it is, it's a very simple algebraic problem, and which you basically show that the path is really the intersection of the cylinder. If you follow the path of the vertex through a transformation, it's transforming to its limit. It continues in the same direction in terms of rotation, but now it moves all the way through. And that path of a single vertex will describe an elliptical intersection of the two cylinders to which the faces are connected to. In other words, the cylinder of this face, the cylinder of this face, the common vertex will pass through the two cylinders, and it will be an ellipse. So it's not a too difficult problem to solve mathematically. Now, this is another example of those rotation, translation, transformations in which you have the face transformation, the vertex transformation, and the edge transformation that was done that way. Recently, you've been seeing that these have been applied in the fields, in this particular case in virology. You'll see the same kind of transformation taking place in this particular virus, and it's a rotation, translation, but the connection happens to be a linkage across the edges of the face. So it's a different type of linkage, but nonetheless the transformation is the same jitterbug type motion that we're familiar with. All right, now another interesting thing that I found is I was doing some work in aerospace, basically. I was working for a firm that does aerospace flight simulation equipment, and we project onto spherical surfaces, and we needed to keep extremely accurate surfaces. We wanted to be able to build structures that were maybe 20 foot in diameter that had a sphericity of less than 1 centimeter, and that's not exactly the easiest thing to do. And one of the main problems we were faced with was we were making them out of composite materials, and when you take the filler materials and the composites and stretch it over a die, you induce stresses into those materials, and they have a tendency to want to take on a saddle shape. So we started looking for ideas about eutectic materials, materials that when you compress them, they compress in all directions. When they expand, so they have a negative Poisson's ratio. And these materials basically do that. When you pull on them, they expand in all directions. So they have a negative Poisson's ratio. So there's some applications that are being done for that. Now the jitterbug led me to another interesting question, and that question is, what is the common volume where the axes, if treated as a cylinder, or the cylinder that the face shares in the process, what is that common volume like? So I started studying what is called the intersection of cylinders. This happens to be the polyhedron. All faces are cylindrical faces that is created from the three mutually perpendicular axes of a cube. the face axes of a cube. So this is the form that starts to fall out of that. Now, in that process, we've looked at the symmetry axis sets, of the edge sets, the face sets, and the vertex sets. And in the process of studying these, we found out we could put them, classify them in 3 groups. And right now I'm going to show you have a group 1, a group 2 set, and a group 3 set of things that can happen in the process. In the group 1 set, basically we have any symmetry axis set or combination sets will define a polysolidohedron by Boolean operations of the intersections of the axi followed by the intersection of a combined set of axes. So down here you'll see the 2 sets of axes, or combined set. You have this set is one axis, you have this set, and basically if we do an intersection of these 2, we get a figure like this. So that gives us a unique polyhedron in the process. And whatever groups of sets that you want to do that with, you can. In the group 2 series, I call those the compound polyhedra. And that is created by Boolean operations of the intersection of the axis of the sets. That's what you have here, the intersection of the axes. All right, then you basically do follow that by a union of the sets. So what you're doing is superimposing one polyhedron inside the other. And you get this kind of a setup when you do that, these kind of figures. In the group 3, basically we have what I refer to as the stellations. And these are a very interesting set in terms of what starts to pop out of these. I mean, I got very excited when I started to see, because they were totally unexpected when they happened. And basically that's a Boolean operation of the union of the axes, or a set, and then you follow that by an intersection of those combined axis sets. And so basically you find a union of this, then you combine those, and basically you have, combine those by an intersection, and you end up with these just absolutely beautiful, beautiful forms. So here's sort of an example of those 3 sets. These are the combined sets, and where they fall in each group depending upon the Boolean operations that you do to this combined sets. All right, so this is a new family of forms just beginning to explored. I'm in the middle of cataloging a lot of these, and so there's a whole bunch of questions that start to come up that I'm sure could interest many, many people to try to define what are the generalizations that are going through here. CD that I passed out to everybody, you will find that there's also on that CD, in addition to this PowerPoint presentation and some illustrations, I've included an excerpt from Your Private Sky called 5 Ways to Dance the Jitterbug. And this was sort of following their theme in Rhythm to Time. The jitterbug transformation is Plato's scenario. The jitterbug is a quantum machine, tensegrity jitterbugs, and space-filling jitterbugs. And what I would like to close with is that those challenges are out there, ranging from the simple to the complex. They appear in all areas of inquiry, just about every field that you can think about. They wait to be, they're just waiting there to meet the challenger, and I want to know if you're going to be the challenger. Thank you.